Hello and welcome to this lecture where we are going to explore some of the main properties of vectors. Broadly speaking, vectors are linear collection of ordered scalars. For example, the coefficients of the restaurant equation can be represented as a vector. Vectors can be represented as a row or as a column. They can also be represented as a point in a Cartesian plane. For example, we can select x1 and x2. And this point here represents the vector. Another representation is an arrow. The origin of the vector is always at the origin of the Cartesian plane, and its tip at the point that represents its coordinates. Notice that in addition to a length, vectors has always orientation and direction. The vector presented as example has 5 dimensions, but we cannot represent 5 dimensions visually. Eventually, we encounter a plot showing a 3-dimensional Cartesian plane, as we can visualize here. But in order to better visualize it, we need movement and rotation to better understand the relationships between the dimensions, since these graphs are usually presented on the screen or a sheet of paper. In mathematical notation, vectors are usually represented with a lowercase letter, in bold or with an arrow on top of them. Now let's remember that in algebra, vectors are rank 1 tensors. In Python, vectors are usually implemented through the NumPy library as an instance of the array class. In this example, the vector is a 1-dimensional array. In neural network libraries such as TensorFlow and PyTorch, a vector is a 1-dimensional tensor. Now that we have reviewed the basic concepts, let's explore some properties. And the first one is norms. Norms are functions that characterize the vector. And here we have L1 norm, which is the sum of absolute coordinates. To calculate L1 norm, we have the following equation. x1 is equal to the sum of xy. These two bars, we are not going to consider if the number is positive or negative. We are going to extract the absolute of the number. Then we sum all the values according to xi. In this example, there are only 2 coordinates, x1 and x2. So we are going to perform the sum considering these values, 8.25 and 7.5. Now that we have the coordinates, we can apply this equation. It is equal to x1 plus x2. It means 7.5 plus 8.25. And the result of L1 norm is 15.75. Notice in the graph that L1 norm can be understood as the distance along the axis, x1 and x2 in this case. This is also called Manhattan distance. We also have L2 norm. that represents the length of the vector. And the equation is as follows. x2, which means L2 norm, is equal to the square root of the values squared. See here that we have letter I, that means the number of coordinates. In this case, we have only x1 and x2. Now let's apply this equation step by step. L2 norm is equal to the square root of the sum of x1 squared plus x2 squared. So we have 7.5 squared plus 8.25 squared. After calculating the square root, the result is 11.14. Since L2 is the most widely used norm in machine learning, it is common to refer it as x without the subscript 2. Notice in the graph that the vector is equal to the hypotenuse of the right triangle with sides equal to x1 and x2. It is from this relationship that the function determines the length of the vector. This distance is called Euclidean distance. In the case you have already studied machine learning algorithms, you know that this distance is widely used in k-nearest neighbor algorithm, and it is also used to calculate similarity between vectors. In machine learning, we hear a lot about L1 and L2 regularization. These regularizations apply the respective norms to smooth cost functions. Cost functions are used to measure the error that the algorithm is making and are used to calculate the corrections to the algorithm parameters, which is performed by optimization algorithms. The most common examples of regularization are linear regressions with L1 or L2 regularization. A linear regression problem tries to find the values of the matrix coefficients A and the vector B that best fit the data X and Y, such that their relation is given by the equation of the line, as you can visualize here. In other words, solving a linear regression implies minimizing the error, which in this case is given by the sum of the residual squares, which is called RSS. This equation refers to the known y values and the y values that are predicted by the linear function at each step of the algorithm's iteration. This is the classic linear regression equation, and we can use lasso regression, which uses L1 norm. We can see that this first part of the equation is the same, but at the end we have the regularization with the addition of a penalty, which is a function of the L1 norm of matrix A. This letter A here is a coefficient informed by the developer that determines the weight of the penalty. This type of regression removes some correlations between attributes, so it zeroes some coefficients. It can be used to feature selection. And here we have the ridge regression that uses L2 norm. See that we have the same equation, and at the end we are using L2 norm. During the implementations, we are going to implement some examples of last regression and ridge regression, so it will be easier to understand. See you next time!